And this is an experiment of actual live recording of note taking at the same time, using this tablet and Autodesk Sketchbook Express. I didn't use this before. I find it, write it down and explaining things better, but I will look into this possibility myself and actually recording the whole thing here and see how the video size is going to be. It's an experiment. Already there was an error, so I begin to like the sensitivity of a tablet and writing here a lot better. So here's, for example, what I'm writing. So let me pause. So this is going to be an experiment geared toward to existence and uniqueness. So existence and uniqueness of a nonlinear first order differential equation. Earlier we made a nice connection with this problem where naturally it rises. Of course, itself is a reasonable question, but with a orthogonal family, it rises naturally. So let's think about orthogonal families of curves. For example, if I have a curve given by this fixed two-variable function, and while I'm varying k as a constant here. Suppose these are the various picture on the right hand side, various pictures of this Cartesian equation while we're varying k. That if you have taken Calc 3, you know these rises from a level curve, or you can use the word contour and all these things. But we have these families we're looking for example, if I start from this point, so I'm putting if I start from this point and try to keep this the curve in orthogonal to this family of the curve when it passes through, it must be something like this. So if I continue it, I have to turn around a little bit so that it's at this point is also orthogonal. I wouldn't go straight like this because it doesn't seem like it's orthogonal, so I have to turn around like this. If I'm just dealing with the three curves, that's one way, kind of going straight. So overall, if I have to sketch it somewhat, it has to come around like this. This seems like the direction of a curve if it starts from here. If it starts from a different the point, and then it's going to be a different turn that you have to make. So it's a fun exercise actually. Once you sketch like a five or six different levels of a curve and try to kind of sketch this orthogonal curve yourself, and that's what we mean by orthogonal families of curves that is orthogonal to this one given here. So we're talking about existence and uniqueness of something. So the question is a given, change the color. So given this family of curves, and is there other curve family of curve like this? Every time if I go back here, every time start a different point, and I have a different curves here. So it's like also it's a family of curves. So if hopefully in this form is there this form, and such that these two things are always crossing and orthogonal, is that this is coming from f of k and this is coming from g of c, and they're intersecting here in a 90-degree angle in terms of their tangent vectors. So that's the existence question that addresses this part right here. So if you look at the differential form of a differential equation, which from f we get fx times dx plus fy times dy equal to 0. This is the differential equation associated with in the differential form associated with this curve right here, and g will be perpendicular to that. So if you think about in terms of the gradient, hopefully we talked about this one, you swap these two things and change the sign of one of the things, so it's rather convenient to put it here, but where you put this negative sign is not very important. Now we have these new differential form and differential equation, so whether this is going to be solvable or not, it's going to answer the existence of Cartesian equation, which is perpendicular to everywhere, orthogonal to everywhere. So how are we going to solve this differential equation? So I moved around the board space a little bit. This is wonderful. I can have a full control after practice a little bit, where I can be and which part of the board I can show and all those stuff. So let's see, when you look at this equation, and usually in the differential form, what you think about is integrating factor. And in our course, we have talked about several techniques of finding integrating factor. Especially we talked about the technique of computing integrating factor in two variable, not only just one variable. Most of the standard textbook focus is just right around there. So it's quite accessible to look at some complicated problem with a two variable integrating factor involved. But what we are turning this one here, this is usually what we do when we're looking for something exact calculation, something exact, like a polynomial, slightly different sense of exact that is associated with the differential form in there. What I mean by is a polynomial and elementary function, so exponential and all that elementary function we have known. So when you are looking for solutions in terms of this type of function that we have known, then this is something that you go for. But in general, we're going to enter the general discussions to say that this is always a solvable. Not through it in terms of integrating factors, but once you know this is solvable, then it is the same thing as the integrating factors. Let me formulate that part. So if you move things around, that you can see this dy over dx from that equation right there I'm pointing is equal to fy up there divided by fx. So these things are in terms of x and y. So this is simply function in terms of x and y, and the left hand side is just a derivative. And when we look at y as a function of x here, so when we look at this equation right here, we usually look at this as a two independent variable, x as a function of t, so this, let me write it better, y is a function of t. That's how we actually look at it. More parametric version. This is actually better in many ways, but this is one way to formulate it, and standard answer to this type of question is known. So here's a y prime written in terms of function of x and y. Does this one have a solution? The answer is yes. This is, big theorem in the theory of a differential equation. So the answer is yes. Once we have a solution to that equation, does that mean that this is exact?